Now that we're experts on graphing the sine function and the cosine function, in this section we want to shift and learn how to graph the other four basic trig functions. So first we're going to focus on y equals tangent of x, the graph of tan x. And again, just like with sine and cosine, if you have no idea what the graph of tangent looks like, what do? We plot some points. So I've started making a table just like we did for sine and cosine. So I've chosen x from minus 3 pi over 2 to 3 pi over 2 by pi over 2s. And again, I chose the quadrantal angles just because they're easy to do. We're going to see that we run into a problem here, so we're going to have to add to it. But, okay, so let me draw my unit circle picture. All right, so we have our unit circle, and what are the points we're using again? That's 1, 0, 0, 1, minus 1, 0, and 0, minus 1. Okay, so again, I'm using the unit circle to find the trig values of the quadrantal angles. Okay, so and again, I just chose some angles that are near 0. Now, where's negative 3 pi over 2 radians? Okay, well, negative pi radians is here to here, and another half, because think of minus 3 halves as minus 1.5 pi, so minus 1 radians, and another half pi radians, so that's here. Now, how do you get tangent from the unit circle? Remember, the first value is cosine, so that's cosine of minus 3 pi over 2 is 0, and sine of minus 3 pi over 2 is 1. Now, how do you get tangent? Remember, tangent, the definition in the unit circle was y over x, or you could say tangent sine over cosine. But what is 1 over 0? Well, that's undefined. So tangent of minus 3 pi over 2 is undefined. Okay, now what about negative pi? Negative pi radians is here. Again, cosine and sine. Tangent 0 over negative 1, which is 0. Negative pi over 2 radians is here. So we're using this point in the unit circle. Again, tangents y over x, which is undefined. 0 radians, we're here. Tangent is sine over cosine, or y over x, so that's 0. Now I think you see what's happening here. Pi over 2 radians is here. Notice I'm going to get the exact same answer here that I got at minus 3 pi over 2, because pi over 2 and minus 3 pi over 2 are coterminal. Coterminal angles are going to have the same trig function values, but it's y over x, which is undefined. Pi radians is here, 0 over minus 1 is 0, and 3 pi over 2 radians is here, and we get undefined again. Okay, so we don't have a lot going for us here. I used, 1, 2, 3, 4, 5, 7 values, and I only have 3 points. Okay, now, so let's kind of sketch what we have, which isn't much. So minus pi over 2 is here, minus pi is here, minus 3 pi over 2, 0, pi over 2, pi, 3 pi over 2. Now, at minus pi, we hit 0, okay? At 0, y value is 0. And at pi, the y value is 0. So that's what we have so far. That's not very much. Now, notice with the sine and cosine graph, we got a value everywhere. There's no undefineds. So at minus 3 pi over 2 and minus pi over 2 and pi over 2 and 3 pi over 2, the function tangent is undefined. Now, we saw when we studied rational functions, just because a function's undefined at an x value, I mean, what could happen with a rational function? You could have a vertical asymptote, or you could have a hole. So I'm just going to cut to the chase here. So for the tangent graph, all these undefineds, we actually have a vertical asymptote. So at negative 3 pi over 2 vertical asymptote, negative pi over 2 vertical asymptote, pi over 2 vertical asymptote, 3 pi over 2 vertical asymptote. I'm going to hopefully convince you in a second that they actually are vertical asymptotes. Now, if we want to, now what was the definition of vertical asymptote? When your function gets close, when your x values get close to, say, pi over 2, the function blows up or blows down. Okay? Now, again, I cut to the chase and told you they're vertical asymptotes, but you could discover it by doing what I'm about to do. So if I add to the table here, let's figure out what the function does close to 3 pi over 2 on the left-hand side. Now, 3 pi over 2 is about 4.712. Okay, so this x value is about 4.712. So if I want to know what the function does just to the left of it, let me pick a number just to the left. It's 4.712 of 4. Let me do 4.712. So if I do 4.712, so that's like right here. And if I take tangent of that, so again, I'm adding points to my table to figure out what this graph looks like. So I'm picking a value very close to 3 pi over 2. And if I take tangent of 4.712, again, if you're following along, make sure you're in radian mode. I got 2,571 if you round. So at this value, 4.712, I'm getting 2570.8. So what does that tell you? The y value is way up here somewhere. Okay. Now that shouldn't surprise you. I told you there's a vertical asymptote here, so you knew the graph was either going to blow up or blow down. Now what's happening over here? So pi over 2 is approximately 1.5707. Okay, so this is 1.57079. Right? I want to pick a value just to the right of that, so say 1.571. So 1.571. So that's going to put me right here. If I take tangent of 1.571, I get negative 4909.8. Again, make sure you're in radian mode. So notice at this value, I'm way down here. Okay? So you can see what the graph is doing. It's blowing up when we get close to 3 pi over 2 on the left. It's blowing down when we get to pi over 2 on just to the right of it. And you could pick some more values and add to the table, but I'll just tell you the graph does something like this. Okay? So you could pick some more points in between here and add to your table. And you could do the same thing here. Pick a number a little bit less than pi over 2. Pick a number a little bit bigger than minus pi over 2. And you'll see you're going to get the same thing again, this branch of the tangent. And same thing over here. Okay, so that's your tangent graph. Okay? Now, so again, we don't want to always have to plot points. So how do you construct the tangent graph from scratch? Okay, you say something important happens every pi over 2, just like the sine and cosine graph. But for tangent, notice you alternate asymptote point, asymptote point, asymptote point, asymptote point. And the points, is 0. It's on the x-axis. Okay? So once you get the asymptotes and the points and you realize that it's these noodle things, the tangent graph, when you go from left to right, you go from bottom to top, right? You're blowing up. Okay? So when I have to sketch the tangent graph, I just say every pi over 2, something important happens. Okay? And then you have to ask yourself, well, what does the tangent graph do on the y-axis? It crosses at 0, 0. There's my point, asymptote, point, point, asymptote, point, asymptote, point. And I know when I go from left to right, the graph is increasing, so it does like this. Right? And same thing over here. Okay, so that's how you construct the tangent graph from scratch, so you don't have to plot points. Something important happens every pi over 2. You alternate asymptote, point. On the y-axis, tangent crosses at 0, 0, just like sine did. And when you go from left to right, the graph is increasing. Okay, so you can reconstruct the tangent graph. Now the next question says, is the graph of tangent periodic? Remember, periodic was, does it have a repeating pattern? Sure, right? Asymptote point, and we increase. Now the question is, what is the period of the tangent graph? Remember, the period is the shortest interval of x values for which the graph repeats. So if I do what I did in the last section, I say, notice from here to here, I could pick this up from minus 3 pi over 2 to pi over 2. I could pick that up and move it over, and the graphs would match. Right? And you could keep going in both directions. Pick this up, put it here, you can reconstruct the graph. The problem is that's not the smallest interval for which that's true. Notice from asymptote to asymptote, right? If I pick that up and move it, it matches. And if I get any smaller than that and move it, it's not going to match. Okay? Because you have to go asymptote to asymptote to get, if I just go asymptote to, here, if I move it, I'm only going to be to here. Okay, it's not going to, the asymptote, if I pick it up and move it from here to here, yeah, it'll go here and I'll have the asymptote in the wrong place. So the smallest distance is from asymptote to asymptote, and how far is that? Well, from minus pi over 2 to pi over 2 is a total distance of pi. So the period of the tangent graph is pi. So if you're at a 0, if you move over pi, you're at another 0. Move over pi, you're at another 0. If you're at a vertical asymptote, move over pi, you're at a vertical asymptote. Move over pi, you're at a vertical asymptote. Okay, so the period of the tangent graph is pi. Now, when I'm doing the sketching here, look at one period of the tangent graph, say minus pi over 2 to pi over 2. If you were going to chop this up into pieces, remember when we did the sine and cosine, we chopped it into 4 pieces because it was high to middle, middle to low, low to middle, and middle to high. If you look at this period from minus pi over 2 to pi over 2, how many pieces would you chop this up into the graph? I'm going to chop it into 2 pieces, the bottom half of the branch and the top half of the branch. Okay, so when we graph the tangent, I'm going to do 2 pieces, not 4. Okay, the next it says, use the graph of tangent to sketch the graph of cotangent. So I could just make a table just like I did here, but I want to use this technique in a little bit. So now I'm trying to sketch y is cotan x. Let me use these same values, minus 3 pi over 2. My scale's not good. Let me try that again. So minus pi over 2, minus pi, minus 3 pi over 2, 0, pi over 2, pi, 3 pi over 2. Okay. Okay. So I'm trying to use the graph of tangent to sketch the graph of cotangent. Again, I could have made a table just like I did before, but I'm trying to explain a technique here. Now, remember, the tan function and the cotan function are reciprocals of one another. So, for example, if I knew tan of theta was 2, cotan of theta would be 1/2. They're reciprocals of one another. Okay? Now, what if tangent of theta is 0? What's the cotangent of theta? Well, 1 over 0 is undefined. So wherever tangent is 0, cotangent's undefined. So tangent is 0 at these 3 values on my graph. So cotangent at those same values is going to be undefined. Cotan of negative pi is going to be undefined. Well, what do you think that's going to mean in terms of the graph of cotan? Well, if cotan of minus pi is undefined, it shouldn't surprise you. You have a vertical asymptote there. Right? Tangent of 0 is 0, so cotan of 0 is undefined. And tan of pi is 0, so cotan of pi is undefined. Okay? Now, we've seen this before. It also should not surprise you. Wherever tangent is a vertical asymptote, where tangent's undefined, cotangent has a 0 there. It's the opposite. So you're going to have a 0 at 3 pi over 2, a 0 pi over 2, a 0 minus pi over 2, a 0 minus 3 pi over 2. Right? It makes sense. Where tangent has a 0, cotan has a vertical asymptote. Where cotan is 0, tan has a vertical asymptote. That shouldn't surprise you. Now let's look at the graph here. Some of the values we picked. Remember, I picked this value right here that was close to 3 pi over 2, and I took tangent of it, and it was huge. It was thousands. Right? Well, if tangent of an angle is huge, when you take cotan of the angle, that's going to be 1 divided by the huge number, which is small. So, I forgot what the number was, but if tangent of this value was, 3,000, cotangent is 1 over 3,000, which is tiny. Okay? So notice just before 3 pi over 2, tangent was huge, cotangent is tiny. Likewise, let's pick a number close to pi, say right here. Tangent is tiny, right? Right? Say tangent of that angle is 1 over 1,000. It's tiny. Well, what's cotangent going to be? Well, the reciprocal of 1 over 1,000 is 1,000. Cotangent's going to be huge. So where tangent is huge, cotangent is small. And where tangent is small, cotangent is huge. So where tangent is small, just a little bit to the right of pi, cotangent's going to be huge. And now you see what's going to happen with the branches of the cotan function, right? Instead of going from low to high, notice we're going from high to low. Right? You could do the same argument here, right? Just to the right of 0, tangent is tiny, which means cotangent is huge. So just to the right of 0, cotangent's huge. And it's going to go like this, etc. Okay? So, how do you sketch the graph of cotangent without plotting points or doing what I just did? Every pi over 2, something's important. We alternate asymptote point, asymptote point, asymptote point, where the points are the x-intercepts. But on the y-axis, cotangent has a vertical asymptote, so you have to keep those straight. Tangent crosses at 0, 0 on the y-axis. Cotangent has a vertical asymptote. But once you realize there's a vertical asymptote here, it's asymptote point, asymptote point, asymptote point, asymptote point. And you have to remember the tangent branches go up when you go from left to right. The cotangent branches decrease when you go from left to right. So same questions as before. Is the graph of cotangent periodic? Yes. What do you think the period is going to be? It shouldn't surprise you. The period of the cotangent graph is exactly the same as the tan graph. It's going to be pi, right? Because from minus pi to 0, you pick it up and move it, you keep matching. And from minus pi to 0 is the distance of pi. And you can't make that any shorter to get that pattern to repeat. And again, how many pieces? Well, if I were to graph this, here's a period. How many pieces am I going to chop this into? Top half and bottom half. I'm going to use 2 pieces. Okay, now let's go back to when we were talking about vertical stretches. Okay, so if I were to graph y is tangent x, y is 5 tangent x, and y is 10 tangent x, remember these are just vertical stretches. Okay, so here's my graph of tan x. Now, just to illustrate what I'm doing here, so at pi over 4, tangent is 1. Pi over 4. Right? At pi over 4, tangent is 1. That's one of our special triangles, right? Tan of pi over 4 is 1. Now, what if I did 5 tan of x? Well, if I plug pi over 4 into here, you're going to get 5 times 1, which is 5. Okay? So at pi over 4, the graph of 5 tangent x, 1, 2, 3, 4, 5, is going to be up here at 5. Tan of 0, 0. 5 tan 0 still be 0. So the graph of 5 tan x is going to be doing this. Okay, so this point at pi over 4, 1 gets stretched to pi over 4, 5. Now what about 10 tan x? If I were to sketch that one, at pi over 4, we'd be up here at 10, and the graph is going to be even steeper, isn't it? Now that's hard to indicate. Notice it was easy to indicate with, sin x, 5 sin x, and 10 sin x. That changed the amplitude. That was easy. You put a tick mark and just said it was at 1 or 5 or 10, right? We changed the amplitude. That's hard to indicate here, so I'm not going to do any examples with the coefficients here except for plus or minus 1, just because it's hard to draw. I mean, it's going to be one of these branches, one of these noodles. It's just going to be stretched, okay? So it's hard to indicate on a graph. So we're just going to, if you had a 5 or a 10, you just make it steeper, right? Just make it steeper. Okay, let's do some examples. Everything we did before still applies. Everything we did with sine and cosine still applies. The vertical shifts work the same. The horizontal shifts work the same. Beware, you may have to factor. Okay. The reflection works the same. You'll see. Let's do an example. We have 2 examples here. So it says sketch the graph of y is negative tangent of 2x minus pi over at least 1 period. Okay. Okay, so it's the same steps we did before with sine and cosine, except for there's no amplitude. Remember, amplitude's a how high and how low for sine and cosine. Tangent and cotangent go up and down forever. There's no amplitude, so don't write amplitude. Okay, so what was the first step when we did graphing of sine and cosine? The first thing to check is, do you need to factor? There's a period change and a horizontal shift. So first we need to factor. I need to factor the 2 out, and you get x minus. Again, there's no 2 to factor out from the pi, so you have to adjust for the 2 in the denominator. Always check your factoring by remultiplying. 2x, 2 times pi over 2, the 2's cancel, you get pi. All right, that's the first step. Now let's do the identifying. Again, there's no amplitude. For tan and cotan, don't write amplitude. But notice there's negative 1 times the trig function. That tells me there's a reflection. Just like before. Okay? Now what about the period? Now how do we find the period of the sine and the cosine graphs? We took 2 pi and divided by the b, where b was the coefficient of the angle. Well, why did we take 2 pi? Because that was the original period of sine and cosine, sine x and cosine x. You do the same thing here, but what is the original period of tangent? The original period of tangent is pi. So it's pi over b. Don't take 2 pi over b. That's for sine and cosine. We're going to take pi over b, and b is the coefficient of x, either here or here. B is 2. Okay, be careful. A common mistake is on the tan and cotan graphs, it's pi over b, the old period divided by b. Now what about the pieces here? Remember with sine and cosine, I took the period and chopped it up into 4 pieces, so I took a fourth of the period. But for tan and cotan, I'm chopping the period into 2 pieces, so I'm going to take half the period. So a half of pi over 2 is pi over 4. Okay, so that's the difference. There's different calculations here versus sine and cosine. So let me review. For sine and cosine, the period was 2 pi divided by b, where b was the coefficient of x, and we took a fourth of the period to get the pieces. For tan and cotan, we're going to take pi, the original period, pi divided by b, where b is the coefficient of x, and I'm going to take half the period to get the pieces because I'm only using 2 pieces here. Okay, so that's different. And again, there's no amplitude. That's another difference. Now, what about the horizontal shift, the phase shift? Again, once you do the factoring, it's not from here, it's from here. This is pi over 2. It's minus, so it's to the right. And there's no vertical shift here. I'm not adding a number to the entire function. So there's no vertical shift here. Again, if you don't write vertical shift, that means there isn't one. Okay, now we're ready to sketch the graph. Okay, so what do we do first? Again, there's no amplitude, so I'm not going to put a scale on the y-axis here. Next is do the horizontal shift. Now, how does the shift compare to the pieces here? You always look at that first to plan ahead. I'm shifting pi over 2 to the right, so I'm going to move pi over 2 to the right. But notice the pieces is half the shift. Okay, so when I shift pi over 2 to the right, I'm actually giving myself room for 2 pieces. So don't just move over a little bit because you've got to squeeze 2 pieces in there. So let me actually make room. Pi over 2 to the right is way over here. And that consists of 2 pieces. So there's a piece here and then a piece back here. Or if you want, here's pi over 2. From here you add or subtract pieces, which is pi over 4. So I can add a pi over 4 or I can subtract a pi over 4. I'm just going to head back to the origin. If I subtract pi over 4 from pi over 2, I'm at pi over 4. Subtract another pi over 4, I'm at 0. There's 2 pieces. Again, for tan and cotan, a period's 2 pieces, so you only need 2 pieces to get a whole period. Okay, then you ask yourself, just like before, on sine and cosine, what does the original tangent graph, y is tan x, do on the y-axis? Tangent crosses at 0, 0 on the original graph, but that got shifted pi over 2 to the right, so that point winds up here. Okay, now let's reconstruct the tangent graph, right? Tangent alternates point, asymptote, point. Right. Now, I'm perfectly happy if you finish the graph here. It's 2 pieces, so you'll get 1 period here. I actually don't, it bothers me to have the vertical asymptote right in the middle. I have a hard time sketching it. Again, if you want to do it, go right on ahead. But I'm going to go ahead and subtract another piece this way. So if I'm at 0 and I subtract a piece, which is pi over 4, that puts me at minus pi over 4. So now I have point, asymptote, asymptote. I like having 1 period between 2 asymptotes. Okay, and now the original tangent graph, which way do the branches run? They run this way, right? When you go from left to right, they increase. But we reflected, so they're going to go the opposite way, like this. And see, now that I've seen that, I can do the half here, right? So if you wanted to just do your graph like this, half of that and half of that, that's perfectly fine. That is 1 period. I just like to be able to do the branch all in one fell swoop. So based on what we have here, is this a true statement? Going back to the original cotan and tan graphs, the graph of cotangent is a reflection over the x-axis of the tangent graph. Is that a true statement? So if you take the tan graph and reflect it over the x-axis, you get the cotan graph, the original one. No, the answer is no, right? The shapes will be the same, but the asymptotes and the zeros are in the wrong place, okay? So what is a true statement? If you reflect the tangent graph over the x-axis and then do a horizontal shift, you can get the cotan graph. Okay, so that would be a true statement. Right? So the procedure is virtually the same. Right? The reflection works the same way. There's no amplitude. The period is pi over b, and you take half of the period for the pieces. Horizontal shift and vertical shift work the same way. Okay, so again, what if I had a coefficient here like 6? Right? What would you do? That would just be a vertical stretch. So you just have to exaggerate the steepness of the graph, okay? But, okay, let's do another one. So that was a tangent. So let's do a cotangent. So the procedure is exactly the same. So the next one says, sketch the graph of y is -2 plus cotangent of 2 times x plus pi over at least one period, okay? Okay, let's do the identifying. Again, there's no amplitude. Where would you find that for sine and cos? Remember, it's the coefficient of the trig function. There's no amplitude for tan and cotan. Notice the coefficient is positive here, so there's no reflection either. All right, so now we're down to the period. Oh, well, okay. The first thing I should have checked, which I didn't, I checked in my head, but I didn't say it out loud. Do we need to factor? The coefficient of x here is 1. The 2 has already been factored, okay? So don't forget to check that. I looked at it and realized I didn't need to do it, so I didn't say anything. Okay, so there's no need to factor here. I already did, there's no reflection. Now the period is the original period of cotangent pi divided by the coefficient of the x, which would be 2. Okay, then how do we do the pieces? The pieces is half the period. Half of pi over 2 is pi over 4. And then the horizontal shift, the phase shift, is pi, which way? Right, there's the pi. It's x plus pi, so it's pi to the left. And then notice -2 is being added. It's not being multiplied. It's being added to the trig function. That's a vertical shift. And we're adding a -2, so that's like subtracting 2, so we're moving down 2. Now, just like with sine and cosine, when I sketch the graph, I'm going to ignore the vertical shift. You do that last anyway. Do horizontal shift first and vertical shift last. I'm going to sketch the graph of cotan of 2 times x plus pi. Then I'm going to do the vertical shift. Okay? Okay, I guess I should have planned ahead here. Let's look how the horizontal shift compares to the pieces. Notice I'm going to shift left pi. The pieces are pi over 4. Notice the shift is 4 times the pieces. 4 times pi over 4 is pi. So when I shift left, if I got to make room for 4 pieces, even though you don't have to sketch 4 pieces here. Remember, only 2 pieces is what we need. All right, so let me give myself some room here. I'm going to sketch more than I need. So when I shift left pi and come all the way out to minus pi, that's 4 pieces. So I could actually just mark the pieces 1, 2, 3, 4, and that's minus pi. Right? When I shift left minus pi, that's 4 pieces. So each of these is a pi over 4. So that's minus pi over 4. Another, that 2 pi over 4 is pi over 2. Another minus pi over 4, that's minus 1 pi over 4, 2 pi over 4, 3 pi over 4, and then 4 pi over 4. Again, I'm doing 2 periods just because I like to have the 0 in there. Okay, and then you ask yourself, what does the original cotan graph do on the y-axis? There's a vertical asymptote there, so that got moved all the way to minus pi. And we alternate asymptote, point, asymptote, point, asymptote. Right? So that, you notice in all 4 of these graphs, sine, cosine, tan, cotan, I always say, what does the graph do on the y-axis? That gets moved or up or down, because once you figure out what that one does, right? I knew that's an asymptote, so I know it's asymptote, point, okay? So that's my little reference point to figure out where to begin. And the cotangent graph, when you go from left to right, comes down. We didn't reflect, so that's going to continue in this direction. And make sure your graph sort of approaches the vertical asymptote. In other words, don't do this and just put some squiggly line in there, right? Actually try to make it approach to some extent. Okay, now this is the graph of y is cotan 2 times x plus pi. I ignored the vertical shift. Okay, so now let me put the vertical shift in here. So we need to go down 2. Now if you have a vertical asymptote and you shift that down 2, it's in the same place. Now you may have to extend, right? You may have to extend your vertical asymptotes. Maybe you didn't make them long enough, right? So I'm going to put a scale on the y-axis. I'm going to move this down 2. Now you can exaggerate. Don't put the -2 here, because then you're going to be right in the middle of all your writing. You can exaggerate. Let me put -2 down here, just to exaggerate. So the vertical asymptotes don't move, but this point comes to here, and this point comes to here. And you just have to put the little curvature, okay? Notice here, this is like a bowl shape, and on the right is like a hill shape. And this is called inflection point if you've had calculus before. All right, so try to make the point here change from a hill shape, a bowl shape to a hill shape. So something like Oop, that's terrible. Let me try that again. Okay, that's a little bit better. Okay, so something like that. So this is the graph, our final answer, -2 plus cotan of 2 times x plus y. Okay, so the procedure's the same, you just have to modify. For the period, it's pi over b, take half of the period for the pieces. Horizontal shift and vertical shift work the same way. You just have to remember, what does the tangent graph do on the y-axis? It crosses at 0, 0. What does the original cotan graph do on the y-axis? You have a vertical asymptote. Okay, so I'm going to do a second video for the other two trig functions.